film on the surface of the lighting.
Yeah, I think well, whatever the substrate you want to use, yes.
So the question is, have you examined this with anything to give us some clues as to what to deposit there so we can make it controlled?
Well, that I would like to do. I was loath to give up the only sample that worked for that purpose initially, and this is fairly new data. I was able to make another sample, and the reproducibility, the ability to make these things on command is far higher than that I've experienced using palladium. So I feel fairly confident that I can make some more of these. And as I acquire an inventory, I'll be really happy to give samples to whomever wishes to examine.
Ed, did you mention anything about the light water? Did you run the same cathode with the light water solution?
Yes, but I haven't, no, not this particular cathode. I haven't run with light water. I would like to do that.
In other words, you're not in a position to say light water would be a safe plant.
No, I'm not in that position. And next year, you may hear me talk about light water being active as well. Well, I mean, other people have found light water to be active after all.
And have you tried switching anode and cathode, because since both are platinum, do you see any change, or you have tried that? Because we observed something like that with platinum and with platinum cathode and platinum anode. By switching, we saw a lot of excess heat. So we didn't produce that very often, but it's something like that.
I haven't tried switching. I have a platinum anode also. The platinum anode, of course, gets oxidized, and it's quite different. I might add, too, and I didn't, that this has been seen. My work is, my observation is totally not, it's not unique. Dash in the United States and Longchamp in France also saw the same effect. So there's certain universality about this at this point. But no, I haven't tried reversing the two at this point.
Have you checked the purity of your electrolyte? In other words, do we have any information at all? You have lithium hydroxide electrolyte?
Yes.
Right? And have you checked well, I'd be overjoyed to help you check the electrolyte impurities to see if, after all, we are depositing those impurities. I've observed that on a number of analyses I've done of old cathodes. And a lot of elements show up on those analyses. Normal deposition of impurity metals that are in the lithium hydroxide that do deposit as a function of time.
Yes.
And, so I would expect them to be there, and maybe a peculiar set of them is giving you this film. It's just a suggestion, and we ought to be able to find out what it is.
Well, I might add one thing. The sample I'm describing here, I really don't have any good feeling for its history because it was used a number of times. And it was sort of dark, and it looked a mess. The second sample that I made that worked was a clean piece of platinum that I electrolyzed for some period of time in lithium sulfate. And when that was taken out of the lithium sulfate solution, and that's what Longchamp used, and put into the lithium deuteroxide, it was active immediately, but not to the level. This went to 800 milliwatts, that one went only to 400 milliwatts, but it showed the same characteristics. You know, the same tendency to want to die, and the same tendency to be resurrected. And, you know, it obviously was playing the same game. Lithium sulfate apparently is able to put down something on the surface that is more effective than I could get by accident.
We reported excess heat from dirty platinum at the 6th International Conference on Cold Fusion, and we have seen it since then, including a cell with light water.
Very good. Well, I guess you can't trust anything anymore, can you?
Professor Stoll, we don't have other questions. I think that we can conclude this, the first step of this section. Thank you very much for your attention.
Coulomb barrier because the screen effect is not enough. The second, how the branch ratio changes. Why there is no strong nuclear radiation accompanied with excess heat. 5 years ago, I proposed the resonant tunneling mechanism to explain these two problems, but this model was based on cold fusion effects. Professor Heinrich Kohler was so kind to suggest me, if you can apply your model to the hot fusion data, then the hot fusion people, the mainstream scientists, will pay attention on your model. I tried. Fortunately, it works, and this model has been published in Physical Review C. Now, I try to present an improved version of this Physical Review C paper. In my mind, the hot fusion and the cold fusion both are sub-area fusion. Because for the hot fusion people, mostly they are dealing with 20 keV. For the solar energy, it's from the center of the sun. It's from P plus P fusion reaction. The energy of them is about 2 keV. And for our cold fusion, mostly we are dealing with minus 10 electron volts. So we are all under the peak of Coulomb barrier. This number, some way is larger, some way is smaller, depend on the radius you cite. But usually it's about 200 keV or 300 keV. So even for the hot fusion people, they didn't overcome the Coulomb barrier by a very hot particle. They are sub-barrier fusion also. Now the question is, when the Coulomb barrier reduces the wave function to a very small number, how can we enhance this probability? So we need the resonance. For the hot fusion people, they are using the D plus T, deuteron plus tritium resonance near 100 keV. That's a sub-barrier resonant tunneling. That's not good. Can we reduce the image? Because I want to show whole the page. Because it cannot see the ordinate. When I see...
Non può ridurre l'immagine?
Better use the old.
This is better.
Yes, use the other one.
Vittorio, puoi aiutare?
Let's go back to the other one. Too big. That's no good.
Indeed, my character is very large. Use this one is better, I think.
Sì, usa,
Try to use this one.
Yeah, use the other one.
rimontagli quell'altro, Antonio.
Because this transparency is prepared for this one. Next time I will prepare this one.
Spegni quell'altro. Ecco, ecco, fatto, fatto.
Okay, that's better.
Good. Good.
Can you see the back seat? Okay? Okay, then I continue. First, we talking about the sub-barrier fusion. Now we talk about resonance, both for hot fusion and cold fusion. There are resonant tunneling because the coulomb barrier peak is here. For the hot fusion, it's here. For the sun, it's here. They are all sub-barrier fusion, but the hot fusion people use the resonant tunneling also at this 100 kV. Look at this D plus T fusion. This is D plus D fusion cross-section. From the resonance here to there, about a factor of 100. This effect keeps even to this energy. From here, a factor of 10, a factor of 100. So the resonant helps both for cold fusion and hot fusion. Now, we try to use the basic nuclear physics to calculate this kind of resonant effect. Here is the Coulomb barrier, just 1/r, and here is the nuclear potential. It's very complicated, but we just use the simple square wave model. Only two parameters, the real part and the imaginary part. The imaginary part describes the fusion reaction. It's an absorption of the incoming wave. So how it resonates? When the incoming wave enters the nuclear well, it will refract. When the refracting wave is in phase with the incoming wave, so every refraction will increase the wave function. So the resonance means the constructive interference. We just put this in mind. We try to see what's the effect of this resonance. This is in the Landau's book. The cross-section can be expressed as 1 minus the S matrix. When the amplitude of this S matrix is less than 1, we have the nuclear reaction cross-section. So this means the S matrix has a complex phase shift to get this number less than 1. So we may assume this phase shift cotangent as a real part and an imaginary part. put this in this formula, we just obtained this cross section. You may notice when this part equal to 0, this is a resonance. At the resonance, the cross section is a function of the imaginary part. If the imaginary part equal to -1, you get the largest for this curve bracket. So indeed, we have all the features of the resonance already here. The first, when this real part is in the right phase, we get this real part equal to 0, then the resonance appears. However, the imaginary part is connected to the imaginary part of the potential. So if this one equal to 0, this one equal to 0, this equal to 0, the fusion reaction rate is 0. But if this one is very, very large and this one is very, very large, then this square will kill the numerator. So the cross section is still 0. So we understand there must be a best imaginary part to get the resonance cross section the largest. What's the physical meaning of this? A lot of electrical engineer here. So I try to use this picture. Here is a radio station. We have 5 radios. They all tune to the exact frequency as the radio station. But their damping is different. From here, 0 damping, to here, the strongest damping. Italian people call it smottamento. That's a damping mechanism. We knew that if the damping is very strong, when the radio station is far away, we can hear nothing. But if the damping is 0, we're supposed to have very good resonance, but we can hear nothing also. Why? Look at this circuit. Here is an oscillating circuit. The antenna gives the signal to the circuit, and the loudspeaker takes away the energy from this resistance. When this frequency is resonant with the radio station, we get the circuit go back and forth, and the current will increase every time. But if this resistance takes away too much energy, every oscillation gets some energy, is less than the energy being taken away, then you kill the resonance. So in this way, if damping is too strong, you have no signal. But if this resistance equal to 0, you have no signal also. So there must be a best damping to get the weak signal. That's a key point of this model. This explains why the imaginary part, that's the absorption in the nuclear well. It cannot be too large, cannot be very small, in order to get the largest cross-section. Now, we have to do more calculation, see how this model is applied to D fusion, D plus T fusion, deuterium plus tritium. All these red cross are experimental data. And this is semi-logarithm schedule. This is the energy. Here is 500 keV. This is 200 electron volts. Here is 1 bar. Here is 5 bar. You can see the red cross drop on the solid line. The solid line is based on our calculation. In order to see this side, we draw it in logarithm schedule again. is still the energy. Here is 10 to the minus 39 barn to here is 5 barns. The total we have 76 data points. How do we calculate this? We need two parameters, the real part of the potential and the imaginary part of the potential. So we can use two parameters. First is the position of resonance, 110 keV, and the height of this peak is 5 barns. Use these two parameters, we can fix the two potentials. With these two potentials, we can calculate the whole cross-section change with the energy. When I present this result at Vienna, the United Nations International Atomic Energy Agency, as an informal presentation there, they were very happy with this result, and they provide me 2 more data here. When I present there, it's 10 to the minus 26 for the 400 electron volts. That's the data set I obtained from the Brookhaven National Nuclear Data Center. The United Nations provided me 2 more data there. When I returned to Beijing, I just calculated them again with the same parameter there. The overlap is very good. And you can see there is a dotted line, blue line. This is the empirical fit formula used by the hot fusion people for more than 28 years. You look at this, each division is about a factor of 10. So at this low energy region, the difference is a factor of 10, and we win the competition. So now you may ask, what's the relation to the cold fusion? Because these are based on the hot fusion data. We try to apply it to the cold fusion. We go back to the first slide. For the hot fusion, this is the beam target model, and we have the traveling wave. For the cold fusion, we are using the thin line potential, and the energy is here. It's a bound state. It's a bound state with a standing wave. So for this case, we use the cross section. For this case, we cannot use the cross section anymore. We use the lifetime of this bound state. We still use an imaginary part for the nuclear potential, but we simplify the Coulomb area by a square well. And here is the lattice well in the host metal. So when this imaginary part appears, this eigenvalue for the energy becomes complex. We will have an imaginary part in the energy. This means there will be a lifetime for the wave function. So we can do the calculation again and see this imaginary part of energy is proportional to a theta minus 1. What is the theta? Theta minus square is the famous gamma factor for the Coulomb barrier. So we prove this numerically and analytically. It's published in the fusion technology. You can look at this simple picture. This direction is the size of the lattice, and this direction is the imaginary part of the nuclear potential. So when we get the resonance its right side, this energy level will overlap with this energy level. Then we get a resonance peak here. However, if the imaginary part is too large this way, we have no resonance. If the imaginary part equal to 0 here, we have no peak. So there is a best imaginary part to get this peak. How many minutes? 5 minutes. 8 minutes, good. The important thing is this application. We have to assume there is an energy level for the D plus D fusion. How can we identify this energy level? Because mostly we couldn't see any neutron or gamma radiation. How can we identify this energy level? Fortunately, Professor Takahashi and Professor Kasagi both proved that there is a 3D reaction. We can use the 3D reaction to identify this D plus D resonant state. If in this target, these neutrons are randomly distributed, when the 150 keV neutron beam injected, mostly we will see the 2D reaction. Very, very little chance to see the 3D reaction. Only in the case 2D stay together long enough time, then we will see the 3D reaction. Fortunately, Professor Takahashi used the T plus helium-3 to identify the 3D reaction. As I understand, Professor Kasagi used another reaction channel to prove there is 3D reaction. No matter what they do, they found an anomalous enhancement for the 3D reaction yield to the 2D reaction yield. Based on their data, we can estimate what's the lifetime of this 2D state. Fortunately, the number is extraordinarily large. It's on the order of 10 to the 4th second, even larger. It's about several hours. Then let's see what's the hot fusion data say. This is a table given by Professor Kuning from Caltech. He gave this part of the table 10 years ago to prove the cold fusion is impossible. But now we use this table to calculate what is a lifetime. For the weak interaction, the P plus P has a lifetime about several hundred seconds. For the electromagnetic radiation, the lifetime is small. And for the nuclear reaction, which produces the neutron, this time even smaller. This is about the bounce time in the nuclear well. So now we are looking for a kind of lifetime even longer than this. What is this? I don't know yet, but I think Professor Henkelstein gave us a frame to find this kind of interaction. The macroscopic and the microscopic covering to find the phonon and the nuclear interaction. I'm working on this. Five minutes? Good. So, this is my summary page. The first both cold and hot fusion are sub-barrier fusion. So both cold and hot fusion rely on resonant tunneling. And the resonant tunneling selects not only the frequency, but also the damping rate. And the fusion reaction rate acts as a damping rate in resonant tunneling. The low energy resonant tunneling selects the slow reaction rate, means very weak damping. And neutron emission reaction is a fast damping, strong damping. So the conclusion is cold fusion has no strong neutron radiation. The problem is, how do we identify the low energy D plus D resonance? Fortunately, we have two data. The first is 3D anomalous yield, means the 2D stayed long enough time. And the most important part is heat after death. It shows a time scale 10 to the 4th second or several hours. This time scale appears at the boiling temperature at 95 degrees, at 2 degrees higher than the room temperature. So this is not a diffusion time scale. And possibly this is a hint for this kind of D plus D resonance. The only question remains is try to produce this kind of resonance. Fortunately, Giuliano Preparata gave us the direction, the coherence in the condensed matter. If we work out this project, then we will have a fusion energy without strong nuclear radiation. Thank you.
As a reaction to your talk, can we say that hot fusions were using wrong theory? So far, the hot fusion worker, were they using wrong theory? Then we implied your talk.
I don't think so. Hot fusion people are correct. I am a hot fusion people also. That's the formula they used for the fusion cross-section, the 5-parameter empirical fit for the dotted line, blue dotted line. Thanks to Professor George Miley, he helped me try to find this old paper. Look at this fusion cross-section theory. In this paper, in 1972, they used 5 empirical parameters to fit the cross-section. It's good, but it is not good enough because it used 5 parameters and the agreement is worse than ours. So I cannot say they are wrong. They are the guidance for me to reach this right direction.
Yours is improvement.
Yes, you are right.
Let's say I wanted to point out that analysis of resonances in fusion reactions formed the basis of the first quantitative models for the fusion reactions. For the DD fusion reaction, Myers in 1938, I think, was the first to try to account for DD fusion from resonant cross-sections. In fact, the model he presented is, here as I can tell, is more or less indistinguishable from these earlier nuclear fusion models. In the case of DD fusion, of course, it didn't get the data. For DT fusion, it did. So it would be comparable to go back to the literature and if nothing else, get proper citations, but also to see the way these things are thought about by very smart folks that worked on this thing for very many years. anyway, it's a very interesting work.
Thank you very much. I need your information for the old literatures. That's great help.
I think the idea of thinking of scattering off of nucleus in a resonant condition is a very useful one. And in fact, that's something that I'm going to talk about in my talk. But it wasn't clear to me. It appears that you don't, you haven't identified a particular reaction that would be associated with cold fusion. It's not. It doesn't seem to be standard DD going to helium-4 with a gamma ray or radiation. Do you have a reaction yet? I mean, I think the framework is good, but do you have a reaction yet that you think is going to be appropriate?
I believe Dr. Makubri had very good answer to this question. It's D plus D with the helium and the excess heat. How this excess heat comes out from the lattice? I'm working on this.
Oh.
Thank you.
I think your potential is the application of your potential to the fusion problem. And I want to know, did you calculate the quantitative value of the fusion reaction in some palladium deuteride, for instance? Did you?
This is an important question. Right now, when I calculated D plus T, it's beam target interaction. So there is no environment. It's a free triton. When I go down to the lattice, I just quantitatively prove there is a resonant peak for the specific imaginary part of the nuclear potential. And I prove the order of the magnitude in theta minus 1. That's the only quantitative result I have got. So I need to work further, try to find where is the real resonance and what's the property and how we can keep the resonance going in the condensed matter. It's a problem for all of us.
Just a comment. To the 10 to 4 seconds, I should mention that it's since many years, we know semi-empirically, it's not a theory, semi-empirically we have 10 to 6 seconds or 10 to 4 seconds for the interaction time. But the second question is then, in this relation, then the picometer distance is important indeed. For the screening, we have our detailed theory. But are you still having then the picometer distance for your 10 to 4, 6 seconds? My question.
This is a very important question. Indeed, I talk about only one of the homework Professor Hora gave me 2 years ago. He assigned another homework. Just try to calculate the size of the DD resonant state. Mostly, we are talking about the resonance. The probability appear in this nuclear well will enhance. So sometimes we will say the atom size is very small, but that's just half the world. Because this part, it will appear also for the DD function. So when we do the average, calculate what's the average distance between these two deuterons, I believe it's much greater than we believed before. So I believe Professor Hora will give us this real data. I didn't complete this homework yet. Sorry, I will do it.
Thank you, Professor Lee.
Thank you.
Professor George Meyer.
I'm going to talk about recent work on thin film electrode experiments. Since we have specialized in thin films over a number of years now as a way to make our own electrodes in a more controlled fashion. I'd like to recognize co-workers Giovanni Selvaghi, Andy Tate, Mike Williams, University of Illinois, Ben Schietta, Heinz Hora. I'm going to divide the talk. I'm going to divide the talk into three sections. First third, I'll review some old data, which I think is important to present here, in that thus far all the concentration has been on deuterium reactions producing helium-4 and gammas. We have worked on an alternate proton-metal reactions producing other reaction products. So these low-energy nuclear reactions, as we're terming them, represent a different regime of cold fusion. And in fact, when you look at the reactions, the DD helium-4, the better known reaction first studied, is listed here, but what we're talking about low-energy nuclear reactions would be reactions where one loads protons into the metal instead of deuterium and ends up with reactions which have an array of reaction products instead of the single helium-4. Sometimes that's been referred to as transmutations, but it's the same thing. Now, our thin film work was instigated by the swimming electron layer theory of putting alternate layers of different metals of different Fermi levels in them together to enhance conditions at the interface where one gets a high electron density. And so, and this theory was pioneered by Professor Hora. The early experiments that we did with this were a great success and failure all at once. At ICCF-8, we recorded results with this type of thin film coatings on a steel substrate, and these heated up, loaded very rapidly, and according to the very brief calculation we were able to do for the period the film lasted, which was order of minutes, we had kilowatts per cubic centimeter produced in the metal. But then the film disintegrated, which is a major problem in this area, is the maintaining integrity of the coated film. But we think we have found ways of doing that. Now, later, in collaboration with Jim Patterson and people at SETI, we worked out a quantitative measurement of the reaction products. And this just shows one of the types of scans that we did with thin film coatings on beads in a Patterson type cell. And this is a low resolution SIMS run, just to illustrate the fact that before, with nickel being the thin film, there's nickel lines and other impurities, this being a scale somewhat proportional to the concentration versus mass. But after the run, there's this whole array of additional products that appear. And the basic question, which, and this was presented in the previous ICCF meetings. The basic question, of course, is, are these impurities? We've had studied that exhaustively. Many different answers against that being impurities. For example, if you take several of the higher yield isotopes, the ratio of the isotope found after a run to that before turns out to be an order of magnitude or several orders of magnitude for silver or copper. Now this was done using neutron activation analysis where the entire system was studied, so that it isn't that there's some hideout of the metal someplace. And also there's a small but statistical significant deviation in the isotope ratios. Well, skipping on in that, there are a whole array of things that we studied over a period of 2 years of that work. And one, we have a null run with a dead electrode. After hearing Ed Storm's talk, I'm a little worried about that one, but we had tried many. At any rate, the bottom line of that is that the type of data that we obtained showed a distribution, a characteristic distribution of this reaction product array, which is characterized by having these peaks at certain mass numbers. There's a large number produced here, here, and in this region, and there. And this seems to be characteristic of many of the other studies that have looked at transmutation products of this type. And we've taken considerable time looking at the systematics of this and potential theoretical explanations. And for example, there seems to be a strong correlation with magic numbers, etc. I'd call your attention to the poster on this subject on Thursday, 001, Professor Hora, and this synthesis of heavy elements will be discussed at that poster. I'd also call attention to the other poster that day, 066, relates to this, which is one I'm giving on the fact that if you take this array of products that's observed, multiplied by binding energies, subtract the initial fuel binding energies, you get a relation which correlates reasonably well with the heat produced in those runs. In other words, this array of products and its measurement is, to this field of LENRs, the equivalent of the measurement of helium-4 in the DD reaction, as has been discussed in the previous talks. So, concluding that review, as I say, this array plays a role similar to helium-4. It's interesting when one has so many products as opposed to just one. There are advantages and disadvantages. This may be, though, an advantage in terms of the fact that in order to predict correctly this strange array, the theory has to have certain characteristics, and so that becomes a very crucial factor. Well, that ends the brief review of the reaction products, and I move to question of thin films. Now, what we did recently, though, was a experiment which was inspired by the work that was done at Frascati with thin wires, and this was done as an attempt to better understand thin films. Thin wires have many characteristics like thin films, one of which is that you can get these high loadings with minimal problems of micro cracking due to stresses and so on, since the stresses can be taken up to some extent. And so the experiment that we did was to try to understand better the relationship between excess heat and the loading. And this experiment, which was done by Giovanni Savaglia, is used a 1 meter 50 micron palladium wire spiraled around a plastic support in the calorimeter. Now, this, you can see the spiral wire here. That's not the palladium wire because the palladium wire is too thin to see. This is the anode. It's the platinum wire that was used as the anode in this experiment. There were two cells used, a reference cell and which had platinum, and a cell which had the spiral palladium wire. And here's a photograph of the two. The calorimetry is modest, but had the insulated cells in a water bath and so on and so forth. The wire was conditioned quite carefully prior to its operation. In other words, it was first stretched, it was carefully annealed several times. The surface has been etched with several different acids and various things. So the preparation of the wire was an important factor. It went into this, and then the loading was begun. The resistance, which was used to measure the loading, using the standard Borowski, or we're calling them Couvry curves for loading, resistance ratio versus loading shown here, was measured using a AC signal superimposed on the DC power input. The AC power input was about 2 orders of magnitude lower than the DC. Incidentally, in this particular experiment, that I'm showing, we use calcium sulfate 10 to the minus 5th moles per liter with D2O. Now, as recall, Dr. Cialini's work at Frascati has shown these types of experiments on. This is from the ASTI proceedings, and it shows in 5,000 second time increments this behavior where after you get loaded and decrease, you get some oscillations, so on this time scale. What we tried to do was expand the time scale to focus on the resistivity oscillation. And so this time scale, you'll note, for example, this is 5 seconds from here to here. And this is a slice of time that's taken about 2 weeks after the loading process began. And you can see that at this particular time, actually, we'd gone over the top of the loading curve and we're coming back down in resistivity, but it started going up again slightly, and then we hit what we'll, for lack of better terminology, call a resistivity oscillation. And you can see this occurred very distinctly over 5 seconds, and then this rapid drop. Concurrently with that, the heat release, which I'll try to superimpose, the heat release, which is this line here and goes up, began at this point, which is something like 3 or 4 seconds before the main oscillation of the resistivity. And this time, the heat to power out, power in, excess power goes up to about 1 watt at this point. And that's with something over about 150 milliwatts in. So this is a very distinctive increase. And in fact, this calorimeter was calibrated such that these data points you see for the temperature excursion, I'll separate them now so it's clear. The temperature excursion was exceedingly rapid. The calorimeter is not calibrated for such a rapid change. If you consider the heat capacity that is contained in the cell in order to heat up to a quasi-steady state of 1 watt, this took about a kilowatt burst of power during that 5 seconds. So it's a very significant power burst, and this interesting actually to look at the heat power in, power out, uncorrected for dissociation and so on, actually over a longer time period. This says 0, but it's not actually at the beginning. There's negative values here because of the dissociation and so on correction, and some strange behavior, and suddenly this large output in simultaneous occurrence with the resistivity oscillation. So, summary of that is this resistivity oscillation and the burst coincide time-wise. This is similar to oscillations that were observed earlier at ENEA. This excess heat was too large to be attributed to a phase change or something of that nature, and the excess heat did stabilize at about 1 watt after this occurrence, and lasted for several hours, at which time broken connection terminated the experiment. In the last 5 minutes, I'd like to change pace to the second topic of thin film work that we were doing, which is related to what I just talked about in theory. And so what we're trying to do is load thin films the same way, but what we attempted at the moment was to develop a sort of demonstration kit that could be developed cheaply and distributed fairly widely. And this kit was based on the concept of putting the thin films on a glass microscope slide. In fact, this glass microscope slide, which is shown here on a cap, is the entire electrode. This portion is the cathode, and this is the anode, and they're all sputtered onto the film. The calorimetry that this all fits into is a fairly simplified thermos bottle type calorimeter, which is shown here, but despite its simplicity, it has a great advantage of having exceedingly high sensitivity. In other words, this particular one, for example, has something like 26 degrees centigrade per watt input, which makes it capable of measuring small powers, which we were trying to do with this demonstration type unit. So we've done a number of different runs of this type. I've just selected one to keep from confusing matters, and this has thin films, copper substrate to provide good bonding to the glass slide, nickel, palladium, and these are all fairly thick for us. These are thousands of angstroms. Normally we've been using 500, but for various reasons went to that. The net result of this, I can show the run for that particular electrode. This is calculated in the percent excess power for that film, which has variations. These are largely due to the fact that this type of cell has, calorimetry has variations due to day-night temperature changes in the laboratory. So a lot of that can be traced to that sort of thing. Some of it's other, but you can see that this averages out somewhere to around 50% or so with this particular run, which lasted a number of days, followed by a change in the input power. The one I showed had about 200 milliwatts input power and 400 milliwatts output. Dropping the input power to about half caused this type of a response. And let's see. So for that particular run, the typical values in were about 270 milliwatts input, 410 out, 120, 200 for the two different power levels used. Excess powers shown here, which if you take that percentage, it's around 40 or 50% excess power for this particular run. Run lasted, producing 57 kilojoules over those two times. Error bars on there. The problem with this type of calorimetry is the calorimeter has a number of uncertainties involved, and the error bars, which were shown on the excess power, included the nominal errors shown here, associated with a variety of different aspects of uncertainty in the cell. And even if you take the maximum error combination, one still has a positive excess power output according to this calculation. So conclusion of that was that with this very simple type of experiment, we're talking about an electrode yay big. The best film combinations produce something like 80 to 110% excess power with 200 milliwatts in. The temperature rises are small in this type of calorimeter. It's something like 0.2 to 0.5 a degree, but that's quite detectable with the sensitivity we have. The problem still remains is we haven't completely cured from ICCF-8 that these films do not always stay on the substrate, and we've been working on ways to overcome that difficulty. So, in conclusion, I would point out, though, that while this the results I showed you seemed very modest when you consider that we only had micrograms of metal involved. This gives a very high power density. And the power density in these thin films, and I think in the wire experiments that were talked about, Frescotti and so on, always turn out to be exceedingly high in terms of watts per gram of palladium or watts per cubic centimeter of metal. And these numbers are something like 10 to 100 times the values for the solid electrode experiments or others that you see. So this means that should problems with this type of electrode be worked out, it's easy to see that a high packing fraction could lead to a high total power. I think the power density is a crucial issue at this point. Thank you.
Ken Schulter suggested that some of the excess heat is from some of these experiments are coming from the production of charge clusters. I'd like to suggest that you include with your experimental work just an ordinary AM radio detuned from a station, because every time you hear a charge cluster produced, you get a crack in the radio. And that might be correlated with that chart you showed where your current was showing quite some jumps around.
Thank you. I have no evidence of charge clusters, and this brings to mind something, when we talk about clusters, that distinguishes our thin film work from much of the other types of work that show transmutations. That is, many of the others have found very localized products, whereas when we've done scans and so on with ours, we've not found this localized behavior, but find the entire electrode probably fairly uniformly covered for action products, plus or minus maybe 30 or 40%, but I mean, these are variations across the electrode. I think that's very important because if you think about what we might call, quote, active sites, what you want to do is have the entire electrode active, and that's what we're trying to get. We don't want the local effects.
I've got George, 2 questions. The first one is probably...
I didn't know what to show them.
The first one is probably really easy to answer. The second one, easy to answer also. The simplified thin films on the microscope slides, how reproducible is the excess heat from those devices? And then the other question is, what is the dimension of the film? How thick is it?
All right. The first question about reproducibility with that, we've done something over a dozen or so runs with different of those, and they've all produced excess power ranging from 20% to 110%.
So that's a dozen?
So we've always gotten excess power. But reproducibility, I think, how do you define reproducibility? And my hope would be it's reproducible by other people, and that has yet to be demonstrated. We're hoping to send some of these out.
Yeah, the materials aspect is key, though, so I think that's what it is. And what about my second question?
What was the second question?
I guess how thick are the films?
Oh, yeah. Well, the one I showed, we had 4,000 angstroms for each layer. We had 5 layers. But normally, I preferred 500 angstroms, and they work better, I think, but it's harder to get them to stick.
Did you have a big, do any light water work at all? Light water electrolytes to see that it went away, or did you try any at all?
Oh, I'm sorry. What I showed you was light. I mixed people up. All the thin film work that I showed here was light water. The wire was heavy water.
Okay. And the second question was calcium sulfate as an electrolyte. It's the first time I've seen that used, and maybe I just haven't noticed it in 11 years, but what was your reasoning for using calcium sulfate as an electrolyte? Maybe
well,
Solana did it too.
It's the Italian way.
Oh, I think maybe he answered my question.
What is the molarity of the electrolyte for the thin wire experiment?
Oh, 10⁻⁵.
question. Sorry. I want to ask, did you introduce a radioactive substance in this multi-layer cathodes to see if there is anything happening?
The question was, did we introduce a radioactive substance?
Yes.
We've collaborated in the past with Jim Patterson on experiments with uranium. And so that was a radioactive electrode. We've thought about putting tracer radioactive isotopes into this, and that's an experiment that I would like to do but have not done.
Thank you.
How do you put down the layers of the thin films? What deposition pattern?
It's complicated to explain here, but we use electron beam sputtering onto the surface. Normally, a 5-layer one may take upwards to a day to do carefully. So it's not that slow, it's not that fast, but we also do annealing. This is very delicate. What we want is, again, Professor Hoare gives homework problems, and he wants one for a swimming electron layer to be perfectly square, perfect interfaces. But if you have a perfect interface, you do not have good bonding. So we try to compromise. In other words, we anneal to the point where we get some interdiffusion, but we try to preserve the interface distinctly. And all the evidence we have to date is that this is a very important factor, because the interface is where all the action is, and we want to preserve that. Did I answer your question, Adam?
I was going to ask, sputter coating doesn't work, or evaporation, or putting down these films?
Well, I think there are various ways of doing it. It's just that we happen to be very experienced with the electron beam sputtering, and so we've been doing that now for 4 years, and we know how to control it. We can do what we want to do with it. And there are many different things you want to do. For example, we have to flare the edges to keep continuity there. It's complicated.
Any more questions? So I thank you very much for
The next reporter will be Dr. Mastromatero. Okay, I will use this one. Hi to everybody. Maybe that I need to present myself because I feel like an outsider here. Where is the button? Okay, good. Because as you can see here, I work in a semiconductor company, big one, and I usually manage processes of making electronic devices. So the idea I had when I knew that the cold fusion may be real into thin film layers, and it seems to be a phenomenon that occurs in the surface of thin films, I imagine a device
like a small semiconductor. And you know that the transistor is an electronic amplifier, so amplifies current, voltage, and so on. So I imagined a device able to amplify the energy. If you look, excuse me if I will annoy you about electronics, but as I said to you before, I'm a little bit outsider here. And if you look at the general partitioning of electronic system or electronic subsystem, you can imagine these 5 blocks. We have a core block where usually is the intelligence. We have an interface for the output and usually an interface for the input. And we have always some power coming from somewhere. Solar cells, batteries, and the main of the houses. And why not to try to integrate that block in a very small device able to supply energy to small appliances. So, due to the results coming from your work mainly, I'm not an expert in nuclear physics, so I imagine that all of your works are getting something through. So I would like to use the best of this kind of work. And what is ideal, we can make a few statements. The ideal amplifier uses as input energy electromagnetic energy, because we can manage very easily. And in most of your experiments, are you really using electromagnetic energy? The output energy seems to be, you proved that the output energy is nuclear and quite clean. So why not include in a system, as in cold fusion experiments, a clean nuclear energy as output? And then the material. You know that in manufacturing integrated circuits, we are condemned to produce millions of pieces, millions. So if we will get the solution to produce millions of batteries, we need to use a simple and cheap material. I don't know, we are using palladium also in our job, but we use with a lot of care palladium because it's very expensive. And putting palladium into integrated circuits is really a problem. We can use it only if we have no alternatives. So I tried to, I don't know, okay, this was the cell that I presented in Vancouver. I presented again in ASTI workshop. This is the layout of the cell. You can see here a serpentine or snake of nickel placed on top of a silicon wafer, but separated from the substrate by silicon dioxide, quite thick silicon dioxide dielectric to avoid the electrical connection to the substrate. And also, on top of this silicon dioxide, I put a polysilicon resistor to be able to heat this small slice of silicon at a high temperature. On top of the heater is the brown color resistor is below the narrow serpentine on top, and it's polysilicon. Polysilicon dioxide used as a heater. On top of the heater, there is a solid dielectric that contains many hydrogen bonds. So there is a solid source of hydrogen just between the heater and the nickel. Okay, we have many pads for the input power, and in Vancouver I showed experiments using DC current, DC power supply. But with DC power supply we cannot measure any amplification because usually the sample is destroyed when some energy is produced. This is the cross-section of the same structure, just a sketch showing the morphology of the layers. We have the nickel on top. The high hydrogen content silicon dielectric is silicon nitride. It's very common to use this layer in the in the semiconductor field. And below that layer there is the heater. And when the solid source is deposited between 300 and 400 degrees, so if we overcome 400 degrees C, we can have release from that source of hydrogen atoms. Or I suppose that when the hydrogen diffuses into the solid, there is always ion, is a positive ion. We used to look at the effects of the hydrogen moving into the silicon because it's a noxious material for us. It decreases the reliability of devices usually. And this is the calibration curve for the cell. Because I have not the temperature, it's not possible to measure easily the temperature of the film. We need a calibration done before starting the test or the experiment. And the nickel shows a change of phase at 360 degrees when it loses the ferromagnetic properties. So it's quite easy to understand how much power we need to reach that temperature. And usually the ratio between the resistance and the R0 resistance is around 3. After that calibration, we can have many different conditions in the experiment. Okay, I would like to show you later the results. And this is what I imagined as energy amplifier device. I showed a small block showing that the actual experiments are done without the feedback. So this is the complete system. It's not already ready to be used. Okay. And first of all, we need to test the material, the core of the system, the reactive material. The material for the reaction, in our case, is thin film of metal, and I would like to use nickel as long as I can. I prepared also experiments using palladium. We need a temperature sensor just to measure the excess, the temperature rising when something occurs into the metal lattice. We need, for the final device, obviously, some thermoelectric converter to get the energy coming from the reaction to the energy storage system and to deliver the energy to some other device. And okay, I was really fascinating thinking into this system from the results coming from two experimenters, two groups. One is the Piantelli and Focardi group in Siena, because they claim, and I visited their lab, and I'm quite sure that they are getting real excess energy from their samples using hydrogen, and they claim that the nickel can absorb at high temperature enough hydrogen to give some reactions, some nuclear reaction inside, because they examined the samples and they found a lot of transmutation inside the material. And the other scientist that fascinated me was Don Borghi, was a physician living in Milan in the 40s. And he worked a lot on the decay of a neutron and on the possible reaction to make neutrons from proton and electrons interactions. And that is the apparatus that Don Borghi used in Recife, in Brazil, from the 1957 till, I don't know, for many years he used an apparatus like this. Is a cold plasma hydrogen, is a klystron system, but not in a vacuum, but filled with hydrogen at low pressure. And actually Don Borghi is passed over because he was ancient at the time. And he claimed, and we have all the results of his experiments, to have produced for many weeks, many days, many years, I don't know exactly, neutrons from the system. So the idea is to concentrate the plasma, the hydrogen plasma, inside the small film of nickel, to have not neutron production, but the ignition of some nuclear reaction chain able to deliver some excess energy. So we can imagine this as a small part of the real sample, and we can have inside all the parameters that you usually manage when you make cold fusion experiments. So we have inside the concentration of hydrogen into nickel. We have the electromagnetic energy is the J is the current density, and is related to the electromagnetic energy we give to the system as input. And this may be considered as an energy generator. If we take as good the cross-section that Don Borghi imagined for the interaction by the electrons and protons, we can have the sigma is the cross-section given by Don Borghi. We can imagine power delivering done by that formula. So we have all the ingredients that you are usually using in your experiments. The old samples that I showed you have this kind of electrical equivalent circuit. To simulate what happens inside the sample, we can imagine, we can translate the thermal parameters into electrical parameters and simulate if this circuitry matches the experimental results. We have the irradiation generator, because at high temperature we need to take into account also the energy lost by the emission
high temperature. The RTH is the thermal resistance of the silicon. The RTH PI silicon is the thermal resistance of the heater, between the heater and the silicon. And the RTH and nickel is the thermal resistance between the nickel itself and the heater. And having a system like this, we have the power in that it is able to put the system at a given temperature. And if we have the switch that delivers in packets the energy with a very short energy pulses, we can have a small rising up of the temperature on the resistor, but not many degrees. And the excess power generator is a generator that includes inside, is given by the formula that I showed to you before. So we can put this kind of circuit into an electronic circuitry simulator and and we can see what happens. So we reduce a lot of the time, the time scale. Otherwise, the simulator goes on for days. So we put seconds instead of minutes, because if we imagine that some hydrogen coming from the solid source goes into the nickel, we can have the hydrogen concentration rising up, we imagine linearly, just to simplify the simulation. And if we look at the curve or the temperature of the sample, we can see that from the steady state temperature, something close to 600 degrees, we rise up to the melting temperature of the nickel layer very fast. Having we can calculate also the hydrogen nickel concentration when the melting occurs, and we have something quite low in terms of concentration of hydrogen into nickel. But you need to consider that the other parameter that switches on the reaction is the electromagnetic energy, means the current. So using a very high current density, it seems that in the experimental results we don't need so high hydrogen concentration to switch on the reaction. One minute, okay. I have many slides. Okay. I will show probably only this. And during one experiment, we had an increase of temperature of the sample without this distraction. So we can calculate the amplification at that point, stopping the experiment, because we saw that the aluminum used as bonding began to melt. The melting temperature of pure aluminum is 660 degrees, and we could calculate the amplification in that case, and we had 1.7. In the case of run out of the reaction, because we cannot stop the reaction easily if we don't have the feedback, we calculated amplification of about 10. Okay, there are many things to say about that, but I will ask to your questions. Thank you very much.
Questions?
So I have annoyed you, really.
Excuse me.
With electronics, you are not so prepared that subject.
How did you measure the content of hydrogen inside the nickel?
We measure with infrared spectrometry. infrared spectrometry is the actual technique used to measure the how many bonds of hydrogen we have inside the film.
It's an in situ measurement.
Would you like to see a spectrometer?
It's not during the measurement, it's after.
No, when we deposit the film, we can check the film and we can check the content of boron, phosphorus, all the ingredients we have inside the film. In this case, we have silicon nitride and silicon H and nitride H bonds. We can measure the number of bonds with an infrared spectrometry. Thank you.
You mentioned a threshold for current density and at these lower loadings. Could you comment on that? What is the threshold and how does it vary, say, with temperature and so on?
Yeah. On all the experiments I did, I saw a big difference in the speed of the reaction using different conditions and different current densities. I can see that approaching 10 to 6 amperes per square centimeter, we can get quite high reaction rate. And I used the vacuum because in the solid source we don't need gas or liquid to load the sample. And I used also the gas in the chamber. And in some cases, I did some measurement in air, covering the nickel with another layer to protect from oxidation. And mainly I did measurements in vacuum.
Maybe I could ask a question.
I forgot to show you the chamber.
Oh.
Okay. If someone would like to look at the sample and the chamber, because from that to here is quite close.
Okay. You use a current density extremely large, so that this regime of pinching effect, maybe you overcome pinching region. Do you think about this aspect about neutron emission? Because you want clean energy, not neutron.
Yes, you are right. With the new samples that I can show you immediately, I probably, in the formula, you can see that there is another parameter important, is the volume of the sample. If you would like to generate energy, you need a volume of the sample. And using low density currents, you can have quite big amount of energy using a quite big volume of the sample. Okay, this is the handle for the sample. In this case, there is a new sample. I showed the old one. The new sample is just a small rod of silicon covered with the layers I mentioned. And in this case, we have palladium on top of this. I'm going to use palladium inside the chamber to load it with hydrogen gas. It's quite simple. We have many electrodes to put the feedback, because I need some tool to detect the temperature. So I will put an infrared temperature detector inside the chamber to look at the temperature when we have some extra energy produced.
Let's see. Do I understand that your heat comes out only during the dynamic process when nickel is being heated up? And with nickel, hydrogen goes in more easily at high temperature than low temperature. So palladium, do I understand what you're doing? That it loads during the process of heating the nickel?
Yes.
And then that presumably generates more heat.
Yes.
So
I usually go on over 400 degrees.
So you're taking, okay. Well, now, nickel is an endothermic hydride. Palladium is going to work the reverse. It's going to deload as temperature goes up. But of course, maybe that will produce, well, I don't know. That will,
Okay.
You don't get the runaway with palladium in principle that you do get with nickel.
Yeah.
So
I suppose so. You're right. So I will use low frequency pulses. So low energy. I don't need to heat to match the palladium, but just to have high density current pulses, just to understand if something occurs also at the low temperatures.
you may not get the phenomenon at all with palladium because it's exothermic. I mean, nickel may have been an ideal choice.
We should see some increase of the temperature. I don't know. Anyway, I didn't test the palladium till now.
What's the absolute power levels?
Excuse me?
What are the absolute power levels we're talking about?
Our level is the old samples 200 milliwatts. Is the input power.
Thank you very much.
with hydrogen and deuterium. The objective, the targets of our job were to load the hydrogen in thin palladium wires up to, I indicate here, 0.97, because we use the Baranowski curve to measure the loading, and this is the limit of that curve. The second step is, this first step is preliminary to the loading of deuterium into palladium wires. I indicated here a limit that we wanted to reach, because is probably a necessary condition in order to have cold fusion. The third objective was the excess heat detection, but I'll say more about this later. The method used was described yesterday by Francesco Scaramuzzi, who originally developed it in Frascati. I want only make a few remarks about our experimental conditions. We had used two different electrolytical cells, one with the volume of 200 milliliters, the other with volume of 400 milliliters. The solution was made with light distilled water or with the commercial heavy water, to which we added hydrochloric acid in the concentration of, in a quantity of 10 to the minus 4 to 10 to the minus 5 moles. The same values for strontium chloride. Sometimes we use also mercury added in less quantity, in particular 10 to the minus 6 or 10 to the minus 7 moles, in order to increase the loading ratio of the wires, or sometimes using more and more mercury added to the solution, we can also succeed in keeping the wire loaded also after the electrolysis. Just, I'm going to describe schematically our experimental setup. These are the schema of our two cells. I call the first axial, the second linear. We use a palladium wire 50 microns in diameter and about 10 centimeters long in both cells. In the first one, there are two wires, the palladium wires and the cathode wire, which is platinum 500 microns in diameter and of the same length of the palladium wires, and they are parallel, almost vertical. The second one is similar, but we have the anode composed by 4 platinum wires disposed in a symmetrical way. They are electrically connected in order to form a unique anode. The use of thin wire was explained just in a lot of talks. It's because it's in order to measure the loading, we use this famous curve, and so we can estimate the loading via measurement of the resistance of the wire. We are interested in exploring the zone that I emphasized here. In particular, for hydrogen, the curve limits to the value 1.43, and we have overcome this value. For deuterium, the limit is 1.6, and this is almost the limit value we have reached. The measurement is done using alternate current that is applied through the wires. The first result that I want to present you are about hydrogen loading. I write here that we have reached the resistance ratio less than 1.25, but with poor reproducibility, but resistance ratio less than 1.4 with very good reproducibility. We can obtain this value almost always. The problem is that the limiting value reached is not always the same. It can vary due to the change of experimental condition and probably due also to the characteristic of the wire. The best result would reach value less than 1.25. I want to show you an example of hydrogen loading in a thin palladium wire. You can see here the time in hour, the relative resistance is black, and the current density is blue. The value of the resistance is corrected by the temperature, but this correction is small. I mean that in our cells, the temperature could vary of about 1 to 5 degrees Celsius. So there could be a small correction on the real relative resistance value of about 0.01 or 0.02. In this case, you can see that after a fast loading, when we reach the maximum about 1.78, the wire loads up to 1.666 very, very fast. And then it slowly go down to the value 1.26 in about 1 day, 24 hours. During this experiment, we kept the current almost constant. The variation are due to the day-night cycle because our current supply was so good. This ratio was maintained for 2 days. After this time, we decided to stop the experiment, but it seems that the loading is very, very stable. The second point is the stabilization of hydrogen loading by the formation of a surface layer of mercury. that can block the hydrogen inside the wire. Here, this is a scanning electron microscope image of a loaded palladium wire with a relative error above error 0 of about 1.41. This is only an estimation of the real of this value, because the surface layer of mercury can decrease the resistance, and so it is necessary to estimate, to make a rough estimation of this error, and can be made in the hypothesis that the superficial layer was composed of pure mercury. This correction led us to this value 1.41. 1.41 is a conservative limit. In this case, the thickness of the layer was about 8 to 10 microns over a diameter of 50 microns. I want to show you also some other example of loaded wire. In this case, we have a thickness of only 1-2 microns, but a worse loading ratio, only about 1.7 of the resistance, and the correction is quite limited, only 2%. This thickness can be controlled based on using different mercury quantity, or give some idea. We used 10 to the minus 5 moles of mercury in our experiment. I show you also a third example with a medium 5-6 microns layer thickness and 1.35 resistance measurement. This possibility to keep the wire loaded also after electrolysis in air permits to measure various, in theory, various physical quantity of the highly loaded palladium. The easiest to measure is the resistance temperature coefficient, and we've done such measurement for the 3 wires I have just shown you. This is the result. There is a sharp increase in this value, as pointed out yesterday by Celani, and this possible indication of a phase transition. Deuterium loading. I write here different behavior in the sense that it is not straightforward to pass from hydrogen to deuterium. In particular, when we use the mercury, there is behavior that could be quite different. In a lot of cases, we obtain that adding a lot of mercury in the solution of a highly loaded deuterium wire, the wire deloads. We don't know why. For hydrogen, this doesn't happen. This is an example of deuterium loading. We have performed various current cycles, but fundamentally we can see that we can reach 1.67 value of the resistance in about 1 day, and then we can go down to a value between 1.6 and 1.65 and maintain it for about 2 days. You can see that when the wire is highly loaded, there are oscillations of the resistance, as shown before by Professor Miley, and this oscillation cannot be observed when the wire is not so highly loaded, and only partially when the loading increases. The last point would be the excess heat detection. but up to now we have only performed a limited number of measurements with a calorimeter that was designed to measure power, much higher power. In this case we use 1-2 watts of input power, and our calorimeter have a limit of 0.5 watts. So we see no excess heat, but it's not so significant if we have to improve our calorimetric system. So we look for some indication of possible heat generation on the wire. Yesterday Chilani saw similar results. We have a medium loaded wire, 1.76. At this point we switch off the current. We see a sudden, in about 30-second decrease of the resistance. A possible explanation is that the wire was to a higher temperature when current was on. And then the wire slowly deloads, only slowly because in this case we used a lot of mercury that blocks deuterium into palladium. When we switch on again the current, we see a little increase of the resistance, but we did not come back to the previous value. Unfortunately, we have saw this effect only once. Another possible indication, this is an example of the variation of the resistance. We have seen this several times. There seems to be a correlation between the increasing of the resistance and a little increase of the cell temperature. These are 3 points where we measure the cell temperature. Our rough calculations show that 0.02 degrees Celsius of increase correspond to 10 joule. These are clearly only indication. In fact, in my conclusion, I indicate only the possibility to reach very high loading with the method developed in Frascati, indicate as limit 0.97, and very high loading, but with more difficult for deuterium loading, above 0.95, and this is important to stress that this is over the limit of 0.85 that is a necessary condition for confusion. For the future, I hope to develop a more precise calorimeter in order to reproduce the challenging result presented here by Professor Miley, Antonio Adelino, and Francesco Scaramuzzi. Thank you very much.
Some questions?
I missed the change in the resistivity changes with temperature that you did on the hydrogen-loaded sample. What happened? Did the DRET go dramatically changing at 0.85? That's my impression, but I didn't really, you went past that a little too fast. No, the change in the coefficient of resistivity with temperature as you load.
Sorry.
I guess you just did that with hydrogen and not with deuterium?
This is for hydrogen, yes.
Hydrogen.
We have not data for deuterium because we didn't succeed in blocking completely deuterium inside palladium.
So what was the change in the case of hydrogen? Do you have that stuff? I'm sorry, I missed it.
This is the change.
The sharp increase in DRDT?
The relative resistance in this case is 1.3. The loading ratio, I extrapolated this value because the curves is the Baranowski curves is only up to 1.43 for the resistance. In this case, the value are down to this value, 1.35.
Thank you.
experience in deloading and reloading these? Is there any hysteresis or what happens?
I'm not sure I understood the user's question. I tried several times to load in different cycles of the with Ethereum, and what I can see is that usually the second and third loading is faster than the first one, but we can reach the previous values quite faster. If I can see you, sorry. In this example, at this point we load by turning off the current, and the second loading was quite faster than the first one. It takes only about 1/4 time.
Since yesterday somebody used 2 votes, I recommend that everybody use only 1 vote. Thank you.
Ed, you proved that you were here.
What's the little flashing thing in the middle of the screen?
The flashing thing says that the tape is about to run out.
That's what I thought.
But actually, that's the preliminary warning. Then it goes very accurate. It's 1, 5 minutes, 4 minutes.
Fantastic.
This thing is so... the focusing is instantaneous. It's just unbelievable. And Barbara, we proved that you're here too.
What?
We proved that you're here too.
Oh, I'm here.
You're on the candy.
How are you feeling?
Not very well.
Are you...
Yes. I think it was because when I sat there, I hit my head yesterday, when I sat there, I hit my head back for an hour and a half. I wasn't really badly, but it annoyed me at the time, and I just think that may have been the